Today I'm presenting my project on machine learning to study patterns in chess games. We'll start by explaining the project, what our objectives are, and the steps we took in designing and implementing the code. Then we'll look at the actual code and the main results that we obtained. Finally, we'll discuss the outcomes of our project, and potential future work to expand on this. Chess is one of the oldest and most popular board games globally, with a rich history. The first literature, Book of the Chess, was published in 840. It contained openings, endings, and other chess problems. However, the large-scale exploration of chess has only caught on recently. Most notably, Stockfish is an open-source project where 9,400 years of CPU time has been spent analysing over 5.6 billion self-play games. Furthermore, platforms like Lichess and Chess.com have improved the accessibility of the game. They provide users with standardised time control formats to play each other in real time. These platforms have enabled the collection of big data in chess that's useful for tools like Stockfish. Finally, the insights we get from chess goes beyond the game. Studies can provide insights into cognition and human behaviour. For example, social learning theory. This is the idea of acquiring new behaviours by imitating others. This is something that could apply in chess and has previously been studied for other games such as Go. Previous research in chess helped to form our motivation for the project. Firstly, modern developments in computer chess demonstrate the potential of big data. Stockfish is the prime example of this. Its alpha-beta pruning and min-max algorithms have led to it currently being the highest rated chess engine. However, competing engines like DeepMind's AlphaZero have previously shown the viability of alternative approaches, such as the Monte Carlo tree search. It beat Stockfish in December 2017 over 100 games with 0 losses. While chess engines have gathered a lot of attention, less attention has been paid to patterns and insights into how people play chess, which is what we'll focus on. Chess has also seen a resurgence in popularity over the last decade, giving us increasing amounts of better quality data to analyse. The Queen's Gambit was released in October 2020 amidst the pandemic, and Netflix announced that a then record 62 million households watched the series within the first 28 days. Chess is seeing a greater presence in social media too. It featured in the most liked Instagram post in 2022 alongside Ronaldo and Messi. In addition, there are numerous sources of chess databases online, such as the Lichess Open Database and the FICS Games Database. The importance of access to big data in chess was highlighted in September 2022 when Hans Niemann was accused of cheating over the table by world champion Magnus Carlsen. This led to an investigation and eventual suspension by Chess.com. The main question for our project is the following. Can we use data mining and machine learning techniques on historical data to discover patterns and insights into how people play chess? While there are many objectives, they can be summarised into 4. First, we want to implement classification models to predict the outcome of chess games. Accurate predictions would provide insights into what factors are the most important in determining the outcome of a game. This could help platforms like Lichess to improve the rating system, thus improving the user experience. We also want to investigate the relationship between the popularity of openings and their outcomes in chess games using linear regression. Identifying clear trends could form the foundation for future investigations into social learning theory and how much other people's preferences affect our own when we play chess. Furthermore, we want to perform clustering of openings by game results. Accurate clusters would allow us to identify openings that are more likely to result in certain outcomes. This could be useful in determining someone's style of play, thus enabling more fine-tuned analysis of matchups between players. Finally, we want to perform clustering in openings by the mean differences of the outcomes between their variations. Openings have variations that change how they are played. For example, the Sicilian defence notably has the dragon variation and the French variation amongst others. We believe that passive openings have smaller mean differences, and vice versa for aggressive openings. Accurate clusters would therefore provide a way to quantify how passive or aggressive an opening is, whereas the chess community currently relies on intuition and experience to make these qualitative assessments. Now we'll go into the steps that we took in designing and implementing our code. We downloaded our data from the Lichess Open Database, focusing on games from 2022. As you can see on the right, each month contains around 30 gigabytes of compressed data, amounting to 2.5 terabytes for the year when uncompressed. This is infeasible, so we sampled 6 million games from each month. We also filtered the data to only include rated blitz and rated rapid games. This is because the time pressure of rated bullet games often results in completely different strategies, and the sample size is much smaller for rated classical games. Our data consists of PGN files. On the right, you can see a snippet of a PGN file containing a chess game played on Lichess. The headers contain the metadata, such as the game mode, who the players were for black and white, their ratings, the opening played, and the game result. Note that the headers are not standardized, so they may vary by data source. The PGN file also contains a list of moves in the game, but our project will focus on analysing the metadata. Our data pipeline, which you can see on the right, transforms the input data into something we can analyse with both pandas and Dask, which is a parallelized form of pandas. For each month, we split the PGN file to enable multiprocessing in our Python script to optimize performance. On my machine, this reduced the runtime from 120 minutes to 20 minutes for each month. We then merge the results from multiprocessing into a single CSV file representing that month. We repeat this process for all 12 months. Next, we merge all the CSV files into a single CSV file for our sample of games in 2022. And finally, we convert the CSV file into Parquet files so that Dask can load it efficiently. We use both decision tree and random forest classifiers with various features to predict game results. This is because they're highly scalable and can handle large datasets like ours efficiently. They're also less sensitive to outliers than other algorithms, which is useful because chess data is very noisy. We use the F1 score as an evaluation metric because it's a good measure of accuracy for imbalanced datasets like ours, where there are fewer draws compared to wins and losses for white. It does so by accounting for balance between precision and recall. We also used accuracy as a secondary metric. Meanwhile, we used a linear regression model to investigate the relationship between the popularity of base openings and game results. This is because it's easy to visualize and interpret. We used the R-squared score and mean absolute error as our metrics. We chose mean absolute error over mean squared error because it's more robust to outliers, which is important because we can evaluate outliers qualitatively in the context of the game later on. Finally, we used k-means clustering to group base openings. As we have a large dataset with unclear labels for groupings, unsupervised learning helps us to identify patterns. It's also highly scalable, and the resultant clusters can be easily visualized in a scatter plot. We used the elbow method to choose the optimal number of clusters based on the WCSS score. We also used the silhouette score to measure the goodness of clusters. We'll now go into the code demonstration, where we'll show our data pipeline in action and briefly go over the results of our analysis. We provided a README to help you understand how our project works. It contains a brief description of the project and installation instructions to ensure that you can run our code. We've also explained how to use PGN extract, which is an external library we use to split PGN files. The usage section provides instructions to reproduce our results. Alternatively, it contains instructions to perform analysis on your own dataset. This section also explains how to perform manual data exploration using one of our provided scripts. As mentioned in the README, we have provided a program to convert the CSV output to an SQLite file. This makes it easy to perform queries on the data, as the CSV file outputs may use too much memory to view directly. Now we'll run through an example of converting PGN files to Parquet. We've downloaded a PGN file from the Lichess Open Database and split it into 6 parts using PGN extract, as mentioned in README. Now we've opened a terminal in the code repository, we'll navigate to the src folder, run the script, and provide the path to the original PGN file. It will take a short time to run before outputting a folder of Parquet files. We can track the progress by keeping an eye on the output of the terminal. The script is now finished. As you can see, it successfully created a merged CSV file alongside a folder of Parquet files for our dataset. This script to merge CSV files provides the auxiliary functions used in a previous program. However, it can also be used as a standalone program if you want to combine datasets for several months, like in our study. You can submit a number of CSV files to merge, and it will then convert the data into a folder of Parquet files. As mentioned in the README, we have provided a program to convert the CSV output to an SQLite file. This makes it easy to perform queries on the data, as the CSV file outputs may use too much memory to view directly. Now we'll look into the Jupyter Notebook where we performed all the analysis. You can see an outline of the notebook on the left. We start by exploring the data and performing feature engineering. Then we go into our 4 machine learning studies. Before doing anything else, we need to import the libraries we use and specify the settings for our seaborn plots. Then we load the data from the folder of Parquet files that we generated earlier behind the scenes. Now we can look at the structure of our data. You can see that we have the metadata of over 40 million games, including data such as the players involved, their ratings, what opening they played, the time control, and the result. We started by visualizing the distribution of player ratings. The plot here shows that it roughly follows a normal distribution, which suggests that central limit theorem is in practice here. Then we looked at the most popular openings by eco-category. Eco-categories group openings generally by how open or closed they are. We can see here that the general player base roughly prefers open games. We also compared how this varies by players in different rating groups. Next, we looked at the most popular base openings. We had to group variations of the same opening together by engineering a base opening column. For example, the Sicilian defence has several variations which would otherwise fragment the data. We looked at this for both the general player base and across rating groups, and found that the Sicilian defence is consistently the most popular opening. We also looked at the rating difference of players matched in a game. We measured this by creating columns for both the actual rating difference between white and black and the relative difference of white to black as a percentage. For each of these metrics, we plotted their distribution and the effect on white win rate. Before implementing our machine learning algorithms, we had to randomly subsample the data to 5 million games to reduce memory usage. Our first machine learning study looked into predicting game results using classifiers. You can see in the outline on the left that we tried both decision tree and random forest classifiers with various features. Our features mostly related to openings and rating difference. We also tried different increments when binning rating differences. As you can see, for each combination we evaluated the accuracy and the F1 score of the classifier to determine the best model. The F1 score was the primary metric that we focused on when evaluating the models. Our best classifier achieved an F1 score of 0.510. It was the decision tree classifier using base opening and relative rating bins with 5% increments as the best features. This was still not a great result, but we will further discuss this later. Next, we investigated whether there's a relationship between the popularity of a base opening and its game results using linear regression. Before this, we had to calculate the proportion of game results per base opening, which you can see in this pivot table. To reduce noise, we only included base openings with over 10,000 games. We also excluded the King's Pawn game and the Queen's Pawn game. These are technically base openings, but they're very generic, and cover a wide range of move sequences, resulting in a lot of noise. You can see in the outline that we created a model for each game result for both the general player base and for each rating group. We used the R-squared score and mean absolute error to evaluate our models. While none of the results were very successful, as they all demonstrated poor metrics, there was a significantly stronger fitness with the lower rated players. This is something we'll discuss in the project outcomes. We also investigated whether we could cluster openings by game results. For this study, we used data from the pivot table about the proportion of game results per base opening. You can see that we optimised the number of clusters using the elbow method. We also recorded a table of silhouette scores to help guide us. The elbow method and the table show that the optimal number of clusters is 4. Therefore, we implemented k-means clustering with 4 clusters, resulting in a silhouette score of 0.478. To show the results, we created a column showing the cluster that each opening belongs to. We also created a scatter plot to visualize this. You can see that there are 4 distinct clusters for white versus black win rate of each opening. However, it was less successful at distinguishing white win rate versus draw rate. We will discuss this further in the project outcomes. Our final study involved using k-means clustering to group openings by the mean difference of results in their variations. First, we had to get the proportion of game results per variation. This is different to the previous pivot table, as there is a many-to-one relationship of opening to base opening. We filtered the results to only include variations with over 5,000 games to reduce noise. We also excluded the King's Pawn game and the Queen's Pawn game base openings. The table here shows how we use the Euclidean distance to calculate the differences in results between variations. We've also shown a couple of examples of the Euclidean distances for variations of the Russian game and the Slav defense. Then we used the elbow method and a table of silhouette scores to find the optimal number of clusters. Based on this, we performed k-means clustering with 3 clusters to achieve a silhouette score of 0.712. To show our results, we created a table showing the base opening, its mean Euclidean distance, and its cluster. We also created a bar chart to show the clusters of each base opening. As you can see, there are 3 distinct clusters. The high silhouette score of 0.712 indicates that the clustering was successful, but we will discuss this in more detail later. Now that we've seen some of the code and results, we will summarise the project outcomes so that we can evaluate whether our project was successful. Our first objective was to implement classification models to predict the outcome of chess games. We implemented both decision tree and random forest classifiers. We've used various features like the base opening and relative rating difference. Across all combinations of features, we saw similar performance between the classifier types. The best F1 score was 0.510. This is a poor result, but it is also a successful negative result by showing us the limitations of our data. Our second objective was to implement a regression model to investigate the relationship between the popularity of openings and the outcomes in chess games. To address this, we used a linear regression model between base opening and each game result, such as white win rate. As you can see on the right, we tested this on different groups of players. As the table shows, the R² score was significantly better for low-rated players than other rating groups. While all models were unsuccessful in isolation, the improvement in R² score as the rating decreases demonstrates that there is a greater element of social learning in lower-rated players. These players typically have less experience and are therefore more likely to follow the crowd. Our third objective was to perform clustering to group openings by their outcomes. We performed k-means clustering to create 4 distinct clusters, as you can see on the right. Our clusters have a silhouette score of 0.479 and a WCSS of 50.827. This study was successful as we grouped openings based on how well they performed for white or black. It provided a starting point to investigate high-rated players who outperform when playing their openings, as they may play them in a unique way that makes them more successful than the general player base. Furthermore, our study provides a mechanism for flagging such players. Our final objective was to perform clustering to group openings by the mean difference of their outcomes in their variations. We performed k-means clustering to create 3 distinct clusters, as you can see on the right. Our clusters achieved a high silhouette score of 0.712 and a WCSS of 61.263. This study was successful in confirming our initial hypothesis that aggressive base openings are more likely to have a large difference between the results of their variations, and vice versa. The clusters provide a mechanism for quantifying the aggressiveness of base openings, which is currently a qualitative and subjective measure. With this in mind, we can evaluate whether we've addressed our main question. Can we use data mining and machine learning techniques on historical data to discover patterns and insights into how people play chess? Based on the previous slides, our project has been very successful, as we completely fulfilled all the objectives in the specification. While our machine learning techniques saw mixed results in isolation, even a negative result successfully provided us with insights into the data by highlighting the limitations of our studies. Despite the success of our project, there were still some limitations. First, it took a long time to collect and process the data, which restricted us to high-level analysis where we only used the metadata of games. This means we missed out on potentially key information. For example, the number of blunders made by each player could have enabled low-level analysis such as how often players blunder in different rating groups. Furthermore, we only used data about games on LiveChess. There are large player bases on other platforms like chess.com with potentially different habits which we could have investigated. In the future, we could expand our data pipeline to include more data sources such as the FICS Games database. This would enable a more diverse dataset and the ability to compare habits of players on different platforms. We could also use data from a longer period to perform time series analysis on the data. For example, how does the popularity of an opening vary with its popularity on Google Trends? Meanwhile, Scoutfish is a tool written with C++ that enables fast queries on very large chess databases. It enables queries like finding all the games where the board state occurs with pieces in a certain position. As it's fast, we could use this for low-level analysis such as exploring endgame move sequences. Similarly, we could integrate Stockfish, whose logo can be seen on the right, into our data pipeline. Stockfish already identifies moves that were blunders, so we could explore this in future studies. For example, can we predict a player's rating based on how often they blunder? Thank you for listening to my presentation. On this slide, I have included references for future reading or detail.